Part B. Why have I asked you to do part B? Well, even though you're like, I'm done, I've just converted it on Desmos, right? There's a really important reason why. I hope you'll see the point in us saying, can we confirm the result again, not just by using technology, but by solving the original equations that we had, the vector equations, okay? So let's do this all together. This is part B. Let's write it here. And I'm going to begin just by writing the two equations that I'm solving, right? So here's my straight line. We already said before, it's 5, 2 plus lambda, negative 2, 3. And then I also have the circle, which we haven't written that as vector form, I don't think, in component form anyway. This is what I've got if I think about the circle. Okay, so I'm going to ball these two together. Now, when solving simultaneously, I'm doing just the same thing as I did with the Cartesian equation. I'm substituting one thing into the other, but it's a bit weird because, you know, this is the arbitrary vector on one side, and this is the arbitrary vector on the other, right? The variable, I should say. So therefore, weirdly, I'm going to substitute r into v. That's what solving simultaneously looks like in this context. Okay, so let's just write that out. So I've got the magnitude there, and just to make it very obvious what I'm doing here, here's the 5, 2 plus lambda, negative 2, 3 that I get from the straight line, and then I've got take away 1, 8 that comes from the circle, and that's the square root of 13. Okay. Now, it looks weird, but on the left-hand side there, what you've really got is it's just vector arithmetic. Like, you don't even need to think about what the geometry of this is, just think about the numbers, right? If you look across the top, you've got all three of the x components there, 5, minus 2 lambda, and then minus 1, and you've also got the y components. So there's no reason why I can't just ball them all up together into one thing. Just think about the constants. What's 5 take away 1? That's 4. And then I've got minus 2 lambda there. Does that make sense? And then looking at the y component, 2 take away 8, that's going to be, oops, sorry about that, negative 6. And then I'm adding 3 lambda. And that's everything all together on the left-hand side. Okay, help me out. What do we do at this point?
You can, oh wait. Oh, you can pull out a factor negative.
Okay, yes, we absolutely can factorize, and I can, because it's a scalar multiple on the top and the bottom. It's going to end up being though a fraction. Like because we don't have a matching scalar to take out of the x component and the y component. Yeah, you can take out, you know, a fraction, and I think that would be, it would make this vector nicer, but then you'd end up with a fraction, right? So I'm actually going to not do that. It does make my numbers a bit bigger, but it's still fine. What can we do with this to start to solve for lambda? Because that's the unknown here.
You want to make it into like a magnitude equation of x squared plus y squared equals
yeah, very good. So this is a magnitude, right? So I can just work that out using Pythagoras, right? And then I might as well square all of that so that I don't have square roots flying around, because there's just a square root on the left, square root on the right. So what I end up with is, here's the x squared, as it were. Here is the y squared. And then here is the distance squared, right? And so I know this is a bit gross, but can you see this is kind of equivalent to us trying to solve the, like, expand out the equation of the circle, right? So therefore here, I mean, there's lots of different things I could do. Why don't we just expand it out, because we haven't done the expansion today. I'm going to pull on this trick that you've seen me do before, which is that I'm going to write these as two separate lines, just so that I can collect like terms a little more easily. So then I've got 36 take away 36 lambda plus 9 lambda squared. Does that look okay to you guys? Yep. So what have I got here? 16 plus 36, that's 52. I get that again. And then I get 13 lambda squared. And then, again, when I said it was equivalent, I wasn't kidding, right? Like, because all the numbers are the same, that's why you're getting the same kind of, oh, look, I've got things that are multiples of 13, right? Let's just tidy this up for a second before I do the division. Let's have our lambda squared out the front, 52 lambda, and I've actually got constants on both sides, right? So I might as well subtract 13 from both sides. That gives me plus 39. Okay, I'll divide through now, and that gives me a nice, neat quadratic in lambda. So can someone tell me the factorization? Fantastic. So that, of course, gives us our two solutions, lambda equals 1 or 3. And remember what lambda is telling me like how far along to go on the line, right? So if you have a think about doing the substitution back into our original equation, I'm actually going to let you continue doing this, but I'll just do it for one just so you can see. When we go into the x components, where's the equation gone? It's here. I'll just grab it so that it's within view. Here it is. Okay, so my x is going to be 5 take away 2, which is 3. And then my y is going to be, what's that? 2 plus 3, right? Which is 5. This is the same 3, 5 point that we got before, and I'll leave it for you to do the working to confirm that you get the negative 1, 11 out of this, okay? Now, just as a final point, so hooray, we confirmed it, right? Actually, sorry, I take it back, 2 final points. My first question to you is, which did you prefer? Did you prefer method A or did you prefer method B? You liked A? That's interesting to me that you liked A, because I've got method B here on screen. This is how long it took. I just want you to compare it with method A. It's about 50% more lines, and I even knew the algebra, right? Now, maybe it's the fact that it leans on like Cartesian stuff, which you know very well. So you get out of the vectors, and then you're like, great, I'll use all the stuff I already know, right? It turns into like a year 11 question, right? So you're like, hooray, okay? However, just objectively, it is less working to do it by vector arithmetic if you're comfortable. So this is a little bit like, you know, there are questions where you can do them in radians or degrees. But when radians are weird in your brain, you're like, I'm just going to convert it in degrees in my brain and then off I go, right? But if you can think about it in radians, it's better. The other thing I wanted to point out, just as a secondary thing, is the lambda equals 1 and lambda equals 3. Just think about what that means. Let's go back to Desmos for a minute, right? What was the, what's it called? What's the position vector that we used to get this line? Do you remember what it was? 5, 2. So it's actually down here. 5, 2. And then we said that the direction vector that was supplied was it 2, negative 2, 3, right? So what is that? That is go 2 units to the left. Sorry, which way is left for you guys? That way? And then 3 units up, right? So think about what that's doing. It goes 2 units to the left and then 3 units up. Can you see this lambda equals 1 means do that direction vector and do it once. Can you see that? That's what produces this, right? And then when you get the other value of lambda, which is lambda equals 3, what does that correspond to? Yeah, do it 3 times instead of once. So you can see there's the second time you do it, and then there's the third time, and that's what gets you to the other side of the circle. So we actually have a diameter here, and that's actually how I chose it, because I knew the numbers would be nice and easy for me, and that's why I had faith that it would simplify, even though you had weird fractions and 13s and stuff like that. Okay, so I just think it's very helpful that not only do you just get numbers out, you're like lambda equals 1, lambda equals 3, good for you. I want you to think geometrically in terms of what that's doing, which is moving you along the line. And you know, just like when we talked about the other place you see a parameter, which is the unit circle, what is changing theta doing? And the answer is it's moving you around the circle. It's sort of shifting from place to place in a continuous way. That's what parameters do.